Hello everybody. Today we are going to go through the guided notes for Learning Target 5.4, which is finding limits at infinity. This is our last learning target of the entire semester. So limits at infinity are talking about when the function is going to the left forever or to the right forever, which is basically looking at the end behavior of functions. And something you talked about in Algebra 2, the polynomial unit, was end behavior. So this is the same exact idea, it's just a different notation for it. So we've got to look at a couple of different things. We're going to look at polynomial functions, we're going to look at rational functions, and find their limits and then kind of combine them. So go ahead and write this down, fill in this part of the guided notes. When we have a polynomial, if the power is even, then the end behavior is going to be positive infinity and positive infinity, or negative infinity and negative infinity. So when it's even, which is squared, fourth, sixth, it's going to positive infinity. When it's odd, it's going to be opposite, right? So for a normal odd function, it's going to go, kind of think of like the line, just the line x. Looks like this, going to go up forever, down forever. These are going to match when it's odd. When you reflect either of these functions, those things change, right? So this one, now it's going down forever from both, and then this one, it flip-flops which one it is. Okay, so when you have a polynomial, what's nice about a polynomial is that when you're taking the limit at infinity, you only have to look at this leading term. You only have to look at the highest degree, and that's going to dictate the end behavior. Because if you think about like a polynomial like this, right, that's a quadratic. That's opening up. So as x approaches negative infinity and goes to the left forever, the function is going up forever, so it's approaching positive infinity. It doesn't matter that there's a plus x there or a plus 1 there. So basically, that is all this is saying, is that when we have a long polynomial, we only have to look at the leading term, the highest degree term, to figure out the end behavior. Okay, so looking at some examples of this, there's kind of two ways you can show your work. But for both of those ways, the first thing you have to do is identify the leading term. The leading term does not mean the first term in the polynomial. It means the highest degree term, right? So here it's x to the fourth. X to the fourth is even, and it's positive. So this is the end behavior it's going to follow. So even though we're going to the negative side, it's still going up forever, so our limit is going to be positive infinity. For this one, okay, our leading term is negative x cubed. That's what we're looking at. So you kind of have two options. You can pull out the negative and then go back to this, right? So some people will just memorize these four and not think about what a negative does, just kind of pull out the negative, say, okay, this is odd. It's positive infinity, so I'm in this situation, and then multiply by the negative to get the negative infinity. I like visualizing these things. That's much easier for me. There's only 4 things you have to memorize for that as well. This, 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 or this. And so I know this is a reflected cubic or reflected odd, so it's going to look like this. And as I go towards positive infinity, that's the right side, it's going down forever. So I get negative infinity. Okay. See if you can do number... Okay, so now we have 3 and 4 here, right? We've got a positive term. We can pull the 6 out, and we're just looking at x squared, which again is a quadratic. We're going up forever, so it's going up, so we get 6. And then in number 4, we also have a negative, pull out a -2. It's odd, so we're going to look like this again because it's negative, and we are going to take the negative side going to the left wherever it's going up. Okay, so this is one way to show your work. Pick out the leading coefficient, sketch it, there's your answer. And then this is kind of the algebraic way to show it, where you rely on these. Okay, here is number 5 and 6, just done very quickly, the visual way. This is kind of the bare minimum amount of work you can show for this type of problem. So go ahead and pause here and make sure you have page 1 filled in. Okay, so the next function we need to learn about is something called the reciprocal function. So this is not something we have graphed before, so you want to make sure you're kind of looking at those. But the reciprocal function is 1 over x, or 1 over x to the nth. And this is actually when n is even. So we need to add that this is when n is odd, and this is when n is even. They're going to follow, the same asymptote. But it's not super important because either way, they're going to approach 0, right? When you are going left forever or right forever, the function is getting closer and closer to 0. And you actually had a question about this on your assignment on Friday, and that's why I put it in there. So you could kind of get used to this idea of if it's going towards a horizontal asymptote, that value is what your limit is. This can be super, super helpful because it lets things go to 0 and we can find the limit of them. And we're actually going to use that in this next section. We're going to use the polynomial idea mixed with the reciprocal function idea to be able to take the limit of more complicated fractions. But first, we'll look at some examples. This is why this works, right? We have a tiny number in the top. Like if you think about this algebraically, you can't actually plug in infinity. It's not a number you can plug in, but conceptually you're thinking, okay, 1 is a tiny number and I'm dividing it by something big that is getting bigger and bigger and bigger. It's going to get closer to 0, right? You did this with exponential functions, right? 1/2, 1/4, 1/16, 1/32, 1/64, and so on and so forth. You're getting closer and closer to 0. Remember, limits are about what you are approaching, not about what the actual value is. So when I do this one, I can separate and take the limits separately. This is going to go to 0 for this reason, and then 7 is just 7, so we get -7. For this one, for this reason, these are both going to go to 0. That is a very important fact. Like it seems kind of pointless here. It's like, oh, it just goes to 0. But it's going to be really, really helpful when we go to take the limit of rational functions. So take a moment and make sure you have these things in your notes. Okay. So from trig, we worked with some rational expressions, rational equations, and a rational function is just when you have a polynomial over a polynomial. And the way we are going to take the limit at infinity of a polynomial over a polynomial is by dividing both the numerator and denominator by the highest power of x that appears in the denominator. Okay, we can then use those polynomial and reciprocal function rules we just learned to actually evaluate the limit. There are 3 different situations you can have with these rational functions, and we're going to look at all 3. While you can kind of memorize a rule for them, you can use that to check your work, but on your test, you're going to need to kind of validate why. So make sure you understand how to show your work here. Okay. So this is the first type of situation you could have. And this is kind of just a reminder of your limit or your exponential rules and why what we're about to do works. So divide both the numerator and denominator by the highest power that appears in the denominator. Super important that we're looking at the denominator. So the highest power in the denominator is x cubed. I divide both the top and bottom by x cubed, which is the same as multiplying by 1 over x cubed. So whichever makes more sense to you. So I write that out, and then I have to simplify each one. And that's where this comes in, right, where you can simplify them. So 6x squared over x cubed is going to be 6 over x. Okay, you can use these two rules, but I like to just kind of think of it, imagine it like this, instead of thinking, oh, 2 minus 5 is x to the negative 3, and then having to think, oh, x to the negative 3 is this. It's just, okay, 2 x's are going to cancel, so you're left with 3 in the bottom. So in this case, we're left with 1 x in the bottom. This case, we're left with 2 x's in the bottom. This case, we're left with no x's. And in this case, nothing simplifies. And so when we use our reciprocal and polynomial rules, we can find the limit of each of those 4 kind of pieces, right? All 3 of these are going to go to 0 because of these rules right here, right? We've got 6 being divided by infinity, and 6 being divided by infinity is going to go to 0. 2 being divided by infinity squared, not that you can actually do that, but thinking conceptually, is going to go to 0. 3 divided by infinity cubed, or the thought of infinity cubed, is going to go to 0. So we're left with 0 plus 0 over 2 plus 0, which is 0 over 2, which is 0. So the limit as we approach negative infinity, right? Notice from up here, it doesn't matter if it's negative or positive infinity, it's going to 0. Really tiny divided by really big negative is still getting close to 0. So our limit in this situation is 0. Okay, that's the last one for this page. So before moving on and flipping, make sure you have this written down. Okay. This is another type of situation you can have, but we're going to use the same rules we used on the front page. We're going to take the highest power in the denominator, which is x squared, divide the top and bottom, and simplify. So we divided everything by x squared. We simplified where we could. X to the 4th divided by x squared is x squared, so that's why we have this. This simplifies to 1. This is a fraction. Now we have to use our polynomial rule as well as our rational rule. So 5x squared, that's a parabola, that's a quadratic, it's even. It's not reflected, so it's going up on both sides. So as we go towards infinity, it's going to go towards infinity. So that part goes towards infinity. Then the 1 stays the 1, and 2 over x squared is going to go to 0. Infinity divided by 1 is infinity. The reason we have to actually write this out is because sometimes this denominator here could be negative, and in that situation, we would then be going to negative infinity. Right, so in this case, we're just dividing by 1, but had this been a negative x squared, that would change the answer to negative infinity, because infinity divided by negative 1 is negative infinity. So that's why we have to kind of see it through, even though the top was infinity. Okay, and that's kind of what I'm alluding to over here. But I guess the other way would be like if this is negative and this is positive, it's still negative infinity, right? Even if it's a number bigger than 1, right? If you take, it's kind of weird, but if you take infinity and divide it by 10, it's still infinity. Infinity over infinity is another indeterminate form, actually. Okay, so that was the second type of problem you could run into. And then this is going to be the third and final type of problem you could run into. And so we do the same process. The numerator we don't really look at, but the denominator, highest power is x cubed. So I divide the top and bottom by x cubed. I simplify my fractions. And when I do that, I then take the limit. I've got two reciprocal functions, two fractions, so both of those are going to go to 0. I'm left with 10 divided by -2, which is -5. Okay. That is actually the same situation as number 13. And you can see I kind of know automatically that the answer is going to be 1/4. And so here are some general rules that you can use to check your answer, but not to show your work. So let's make sure, let's maybe write that down. Can be used to check answer, not as showing work. Because this is maybe something, you know, once you're graphing and you're sketching polynomials and rational functions, and you're looking at end behavior for that reason, we could do the shortcut, but the whole point of this unit is testing your ability to, you know, find the limits at infinity. So we need to do more than just memorize rules. But the rules can help you to double check your answer and make sure your answer makes sense. So here they are. If the degree of P is less than the degree of Q, then the limit is always 0. Okay. If the degree of P, which is the top polynomial, is greater than the degree of Q, then it's going to be plus or minus infinity. And then if the degree of P equals the degree of Q, then the limit is a ratio of the leading coefficients, essentially. So the leading coefficient of P divided by the leading coefficient of Q. Okay? That is your notes for this learning target. Please pause and make sure you have this written down. Okay, lastly, your homework is just this entire page, okay, 1 through 10. Make sure that you're showing your work to evaluate them. It's really only 9 and 10 that are, you know, the longer ones. The first 6 are simply polynomials, so you should just be able to do, you know, some sketches with the leading coefficients and figure out what the end behavior is. These are the reciprocal functions, and then these are the ones that just take a couple more steps. Okay, that's all I have for you today. Please make sure this packet is filled in before you come to class tomorrow. We'll do a little bit more practice on 5.3 and 5.4 together. Your Unit 3 corrections are due. Remember, the Unit 3 retake is Wednesday, and your Unit 5 test is Thursday. Please email me with any questions you might have, exclamation.